Okay, let's go ahead and start going over this. So before we went on break, I've given you guys a couple of things on area. Again, as far as area is concerned, we spent a little over a week on it. And I know that doesn't seem like a lot of time, but most of the area ideas and concepts are considered a prereq. So we've done them previous years, we've introduced them, we're going to use them a whole lot more. All right. So now we are going to get into three-dimensional solids. We're going to be looking at surface area, we're going to be looking at volume. And before we do those, we do have to use the area formulas we went over the week before, right? Quite a bit. Now, that sheet that I gave you before we went on break that had all the area formulas and stuff, if you don't have that filled out, make sure you go back, get it filled out. I'm going to let you use that for the next few weeks as we're doing problems, because most of the formulas that we're going to do for both surface area and volume are going to require you to do some type of normal area formula first, or as part of the equation. The paper I gave you yesterday, it was a review from chapter 11 of all the areas that we had done. So I'm going to go through not all the problems, but like the first. How many problems let's see. We go through the first 11 problems on here with you guys. Now, there are some things towards the end with similar figures that I'm not going to spend time on yet, because after we've done three-dimensional solids, then we'll talk about area and volume for three-dimensional solids, three-dimensional similar figures. And we'll hit on that a little bit more of that. So we already did some similarity stuff back at the beginning of third quarter, but we'll hit on that again when we get to the end of this chapter. So I'm going to go over some of these with you. Now, I did not post a spot for this on Canvas yet. I want to go over these 11 problems. After we do that, you want to post it to Canvas as assignment grade, that's fine. But I would like you to also try the back side if you haven't already. But again, why do you over these first? So, number one. Again, in order to do any of these problems, you have to recognize what formula you're going to use first. So, the first one is dealing with parallelogram. Well, what formula can we use for parallelogram? Area. Area. Equals base times height. Now, on this one, are we given base and height? So that's the next question you have to ask. You have to first know what formula we're using, and then we have to know, do we have all the information we need to plug in? So do we have base and height here? Yeah. All right. So this 12.5 could be our base, and then the 5 can act as our height. And height is always perpendicular to our bases. Now, on this one, it's just a matter of plugging those two in. So we have area equals, yes, please, 5 times 12.5. Now, it doesn't actually matter which one you plug in first, whether you do the base first or the height first. So you can do it in either order. But we're multiplying those two values together. And when you multiply those two values together, we get 62.5. Now, this is area, and you'll notice all the answers in the section include our units squared. Because every single time we do area, we should have units squared. The two-dimensional measurement, so it should be in square units. All right, number 2, find the area of a parallelogram. Again, they gave us parallelogram, but did they give us the two pieces that we needed right away? First glance, it looks like they didn't. All right, what piece do we have that we can plug into the formula? We have a base. So this 7.5, that could be our base. This dotted line here is going to be our height. So we need the length of that. What did they give us so that we could find the length of the height? It's an angle. All right. So they told us this was 45. So how could you use that to find the height? And there's multiple ways that you could do this. So Give me one idea. Dig it? So you could do a 45, 45, 90 right triangle. All right, so one of the properties from our earlier chapter, we got 45, 45, 90. The two legs were what to each other? Congruent. So this is x, this is x. And our hypotenuse is x times the square root of 2. Now, on this one, 6 is one of our legs. The height is our other leg. So our height is actually what? 6. We don't actually have a lot of work to do there. So maybe you can accidentally plug this in the equation correctly because those two pieces were the same length. So we have area equals base times height. So 7.5 times 6 and 7.5 times 6. Again, it is in inches squared. All right, the next one, different formula. Find the area of a trapezoid. What's the formula for area of a trapezoid? I know it's only the second day after this run road. I know here is it. B1 plus B2 times height. Now, again, the way that I said to remember this, the first part of this, 1/2 B1 plus B2, that's essentially doing the average of the two bases. So the average of two bases times the height. Doesn't matter which one you call B1, B2. So I'm going to call this B1. I'm going to call this one B2. If you reverse that, that's fine. And that'll be my height. Do I have all the parts I need? Yes. So we can plug in. We have area equals 1/2, 21 plus 12.5 times 5. Again, if you want to, you can plug it straight into the calculator from there. If you want to simplify it a little bit first, that's fine too. Again, that is 5 times 33.5 times 5 gives us what? So, okay. All right. Again, each one of these is a little bit different. Number 4, now we're looking at height. Again, different formula. What formula are we going to use here? How do we find area of height? One B2. One half D1, D2. Now, what D1 and D2 stand for? Well, not distance. So D1, D2 stand for the diagonals. Now, you know the length of those diagonals? Yeah, they label on the outside of the figure, but those are going to be the lengths of those two diagonals. So we know both of them. All we have to do is plug it in. Area equals 1/2. Yeah, it doesn't matter which one we call D1, which one we call D2. 5, that was. So 1/2 of 4 is 2. 2 times 9.5 is going to be 19. All right, number 5, find the area of the rhombus. Round to the nearest 10. So there are two formulas that we could use for a rhombus. The first off, a rhombus is definitely a parallelogram, so we could use base times height. You have base and height? Yeah, do you have those in that figure? You have base and height there? No. One of these sides would have to be my base. I don't have any of the sides. So again, 1/2. Sorry, base times height could work, but in this case, we don't have that information. What was the other formula that we could use for a rhombus? It was the same as a kite, 1/2 d1 d2. Because again, here the diagonals are perpendicular to each other in a rhombus. So we can use that same formula that we had for our kite. So 1/2 d1 d2. So plug in those parts. Now, they did not give us the entire length. But going back to quadrilaterals, we should know some properties about the lengths in that quadrilateral. So those diagonals do what to each other? They intersect how? One more specific than just intersect. For a key word. They intersect, they bisect. Right? They bisect each other. They split each other in half. Right. These two are congruent, those two are congruent. We know the lengths of the entire thing. Because if that's 5, the whole thing is 10. If this is 5.6, and that's also 5.6, the whole thing is 11.2. We know our lengths. We can plug them in. Area equals 1/2 d1 d2. Again, doesn't matter which one you plug in first. 11.2 times 10. 1/2 of 11.2 is 6. 6 times 10 is 56. Any questions on those first 5? All right, item number 6. The height of the parallelogram is 6 feet more than its base. If the area of the parallelogram is 160 square feet, find the length of its base. So this one's a little bit different. They're not asking us to find the area, they're asking us to find a missing piece. Now, some of these are challenging. 6 and 7 were very challenging because they required some extra knowledge. Number 6 actually turns into a little bit of a quadratic. All right. How does this get set up though in the first place? Well, we have height of a parallelogram is 6 feet. So we know that this piece is my height. I'm sorry, 6 feet more than its base. I lied. That is base plus 6 is going to give us our height. Right. They know that the area is 160. We know our formula from before is area equals base times height. So that's what we know going in. I have a value I can plug in for A. I have 2 values to plug in for H. I don't have anything for B, but we can rewrite that. So we have A is 160. H, I'm using parentheses to plug that one in, is B plus 6. And this is where it turns quadratic. If I simplify this, B is going to be distributed to both those values. Now, like I said before, for the FSA, they don't do a lot of quadratic problems. So I usually try to avoid a lot of the quadratics. Where they use the quadratics is usually in equation for a circle, which we did, what was that, 3-4 weeks ago now. When we had a quadratic, we had to equation for a circle in standard form. Well, since that's what we've already used this year, and that's the only type of project that we've done this year, I'm going to use that again for this problem. All right, so we can solve this by completing a square. I'm going to go ahead and rewrite it so that this part's on this side first, and that part's over on that side, just so it looks the same as we had in the other section. Again, when we complete the square, we are going to have to add a value on here to make this side a perfect square trinomial. We don't know what that value is just yet. The other side, we have the 160. And whatever we add to the one side, we have to add to the other. So now, what goes in that space? Well, it's whatever the second value is. What do we have to do with that second value? Divide by 2, and then square. So 6 divided by 2 is 3. 3 squared is 9. That is now a perfect square trinomial. Again, the way you complete a square is you take the middle value here, divide it by 2, and square it. So we got 9. So if we added 9 to that side, balance our equation, add it to the other side. Now, if you remember from that other section, we did this for a reason. So that we can factor this into a perfect square, which is now going to be a binomial that is squared. This first term, again, we're taking that, taking square root of it. So square root of b squared is just b. Square of the last term is 3, and a sign from the middle is a plus sign. On the other side, when we add those together, that actually gives us a perfect square. So in order to solve this problem, I can go ahead and get rid of that square by square rooting both sides. And I can now have b plus 3 equals the square root of 169. Now, if I square root something while solving like this, I get 2 values, a positive and a negative. Going back to algebra, I'm going to be dealing with a length. So can I have a negative length? No. So really, we only need to worry about the positive number here. But that's perfect square. What is the square root of 169? 13. Yeah. All right. Thank you. All right. Then we got the 3. Move that over. Subtract it off, and you're left with b is 10. That's right. I know that's a harder problem. All right. Not every problem in this section is going to be as easy as the one at the top. And even in the next section coming up, we might have some things that are a little bit more challenging. Like I said before, I'm not going to give you a whole lot of things dealing with projects. The FSA doesn't use a lot of projects on it. We will see projects again a lot more in Algebra 2 next year, but don't need doing a lot in. All right, for number 7, this one is also a challenging one. They're giving us a regular octagon. Now, there are 2 formulas that you could use to do this problem. Somebody tell me one of the formulas that we could use for a regular octagon. Look down at some formulas. 1/2. So either 1/2 ASA or the other one, 1/2 AP. Now, it gave me perimeter, so most likely I can just go to the bottom one. But I am missing something. I don't know the A. I don't know my half though. Right? Again, we're coming back from spring break. I've had a whole 10 days to forget everything. But when we draw the regular polygon, half comes the distance from the center to the side of our figure. Now, on here, I do myself an octagon. And the first thing I'm going to do is split it up into equal triangles. reason why I'm doing this is because around the center, I know I have how many degrees? Around any single point, this how many degrees? Alright, so it's 360 degrees around the same point. I just split this into 8 equal pieces because it's an octagon. So each one of those top angles is 45. Now, I need the apothem, which could be the height of any one of these triangles. And it's the distance from the center to the side of my figure. It's my apothem. That's A. That's the piece I need. I know this entire angle on any one of these is 45. So what's this little angle at the top now that I do my apothem? 45 is that's this angle here. 1, 2, 5. All right. Other things that we know the entire thing has a perimeter of 96. So on this problem, well, if the whole thing is 96, can you figure out one side? Yeah, it's regular. Regular means that all sides are what? Equal, congruent. Yeah, either one of those words work. So we have 96 divided up evenly into 8 sides. 96 divided by 8 is 12. So every single one of these sides is 12. So for this apothem here, this apothem is splitting this side so that this side is 6. Now, I know this seems like a lot of unnecessary work, but what we're looking for is that apothem. And if you remember when we did our regular polygons before break, there's a couple different things that can come into play in order to find our apothem. It's usually either a special right triangle, Pythagorean theorem, or trig. On this one, we only know this one side, so it can't be Pythagorean theorem. We don't have a special right triangle because that's 22.5 there. So this is a trig problem. So we have an angle, we have a side, which is our opposite side, and then we're looking for our apothem, which is our adjacent side. So we're using trig. Which one of our trig ratios uses both opposite and adjacent? Right now, see, sum, whole, 50, up, another 50. Tripping, so. Which one uses both O and A? Tangent. So that's the one that we have to use here to get our apothem. Tangent of 22.5 equals opposite over adjacent. All right. Normally what I would say to do at this point, you want to get 8 to the other side, so multiply it over, and we can divide by tangent 22.5. I am going to show you one other way that you could do this. All right. It was something that another teacher was doing for some of their students, and I kind of liked it, so I'm going to show it as an option here. Tangent of 22.5, remember, that is an actual ratio. There's a number there. So if you want to do that number, the very start, 22.5, find tangent, you can find that number. That's 0.414, and you should always keep extra decimals before getting to the end of the problem. So 0.4142. Now, that's our value. We can take that, make a fraction, put it over 1, and we can cross multiply. That might be an easier way for you guys to do this because it's always the same steps every time. That's why I kind of like this. So if you do your ratio, get your value of what that ratio is first from your calculator, and then cross multiply. So 1 times 6 is 6. On the other side, this times A is going to be same value times A. And then we're just dividing that off. Now, are you still essentially doing the same thing as before? Yes. It's just another way to look at it. So 6 divided by 0.4142. All right. And yes, that's a lot of work, and we're not actually quite to the answer yet. But we're almost there. Remember, the whole reason why I did this was to figure out that piece to plug in. And I know we took like the same length as like 3 other problems in order to get here. What's my formula again? 96. So multiply it out. Again, not every problem is going to be that difficult, but there are going to be some. And are we going to have to use trigger in the next section? Yeah. We're going to have to use special right triangles. Yeah. Like I've been saying, everything that we did in third quarter, it comes up again in the later sections. So it continues to build. All right. On 8. 8, you can choose to do this many ways. We have a triangle. You can just simply do base times height. You could look at, all right, it's an equilateral triangle. It's a regular polygon. You could do something like we did on the last problem and find the apothem and do it that way. Or when we talk about a triangle, there's actually 2 formulas. The easiest way to do number 8 is actually not base times height. It's the other formula that we have. What's the other formula for a triangle that we have? Area of a triangle using SAS, side angle side. What are all the sides in a three-dimensional triangle or in a square triangle? They're all the same. They're all congruent. So one side is 14, they're all 14. What are all the angles? All the angles are 6 degrees. Our formula using side angle side was 1/2 sine of C. This was 2 sides and included angle. So we have everything we need to plug in to this formula. And you can plug it straight into your calculator. You don't have to do any extra work. Put that in your calculator. You get 8. Now, is that the only way to do that problem? No. You have options. Like I said before, can we give you 1/2 base times height? Yeah. Yeah, it's a triangle. It's 60 degrees. Drawing the height, this turns into a 30, 69 triangle. So this is 14, this is 7, and the height is then 7.5 or 3. Our special arc triangle. And you can plug in that way as well. 1/2. This is 14. The height is 7.5 or 3. Did you get the same answer? Yeah. Yeah. Multiple ways. All right. So those 3 were probably the hardest ones on this entire worksheet. So now that we're past those, let's do a couple on the next piece there. Like I said, I'm only going up to 11 today. Want to try it if you want. All right. So 9 through 11 are fairly easy compared to what we just did. If you try it, great. I tried it. Yeah. Oh, yeah. If you did it, I'd like you to try it all. All right. Number 9, area of a circle. What's our formula for area of a circle? Now, there's another formula that you need to know for this one, though, because they didn't tell us our dimensions, they told us the circumference. Yeah, so. Okay. Sorry, guys. So again, area of circle, pi r squared. This one also was giving you circumference though, so you have to know your circumference one. So circumference from our previous section was one of two things, either pi times diameter, or we could have also done 2 pi r. Area, even though I said circumference. Okay. Now, since they're telling us the circumference is 20 pi, we should already know one of our dimensions from that statement. Because one of these statements is just times pi. So we have diameter times pi, circumference. So that 20 is actually our what? It's our diameter. So if we know our diameter is 20, then our radius must be 10. So plug in, we have equals pi 10 squared. Now, when you multiply that, that's 10 squared is 100. So we get 100 pi. Or if we multiply out pi, we get 314. What's our answer? What's our answer? A, B, C, or D? Which one? B? Now, it didn't say what to leave your answer in terms of pi or round, but if you look at all the answer choices, it left pi on. Okay? When you're dealing with area for a circle, or any circle forming for that matter, you could leave things in exact values or in terms of pi. All these answers are in terms of pi. So we could have stopped here at 100 pi, that would have been our answer. If we multiplied out pi, this is now a rounded answer, but pi is gone at that point in time. So it's not the same as B. D is our correct answer. All right. Number 10. What's the area of the shaded sector? The only difference between 9 and 10 when it comes to our formula is now this one is only using part of a circle. So this is our formula for an entire circle. If you're just doing part of a circle, which is a sector, you're doing the measure over 360 times pi r squared. So the fraction of the circle you're using, here told us this is 70 degrees. So plug it into our formula, 70 over 360 times pi r is 25 squared. Just plugging the whole thing into the calculator. So again, 70 divided by 360 times pi times 25 squared is now all of our answers. Do you have decimals there? There's no pi, so this is that. Oh yeah, that was an 8. Copy wrong. And then the last one we're going to do right now, number 11. So we had a composite figure. A composite figure, it's just a figure that's made up of more than one shape. So in this one, we have a rectangle, and then we have a semicircle cut out. So again, you can either have two shapes that you have to add together, you have two shapes where you have to subtract one from the other. On this one, we're taking the area of the rectangle, which we're going to find by doing base times height. And then we're going to have to subtract off the area of that semicircle, which would be 1/2 pi r squared. So base times height, 9 times 4, that's 36. On this one, the radius of the whole distance across the 4, the radius is 2, 1/2 pi 2 squared. 2 squared is 4, half of 4 is 2. 2 times 3.14 is 6.28. Subtract the 2, that leaves us with 29.7. Again, we're going to be doing a lot more area as we go along. So tomorrow we're going to start looking at 3-dimensional shapes. And we are going to have to do more area within that section. Yeah, hold on one second.